Okay, so let's go ahead and see some precipitation reactions and how we're going to write a balanced molecular, total ionic and net ionic equations and identify the spectator ions. Now we have potassium fluoride and strontium nitrate. So what you need to do, predict whether or not a reaction occurs when each of the following pairs of solutions are mixed. If a reaction does occur, write balanced molecular, total ionic and net ionic equations and identify the spectator ions. So the first one is potassium fluoride and strontium nitrate. Now we need to know how to write potassium fluoride. So potassium is in group 1. It has +1 charge and fluoride is group 7 -1. So when you write the formula, you will be writing it as Kf, potassium fluoride. And then we have strontium nitrate. So strontium is in group 2. So it will make +2 charge and nitrate is -1. So when you crisscross the charges, -1, one goes over here, so then you will have your formula as strontium nitrate. Okay, so that's how you find the proper formulas. And then we need to know how to write the balanced equation. Once you figure that out, let's see how to write the molecular formulas for the products. Potassium fluoride plus strontium nitrate. Excuse me. And what are the products that we're going to form? Remember, a plus sign is going to react with the negative ones. So it's going to form KNO3, potassium nitrate, plus strontium fluoride. Now again, potassium is +1, nitrate -1. So formula is KNO3. Strontium +2. Strontium is +2. Fluoride is -1. When you crisscross, so the formula going to be SrF2. Okay, and then we need to know whether this reaction is balanced. So if you balance it, there is 2 fluoride over here. So then you need to put 2 right there. Now the potassium became 2. And then you put 2 in front of this potassium. So there are 2 nitrates in potassium nitrate. And then in strontium nitrate, you already have 2. Now we can see it's balanced. And then we need to know, we make any of these reactants or products are solids. So potassium fluoride. So you can refer to the solubility chart that I showed you earlier. And if you refer to that chart over here, this is how you're going to look at it. All common compounds of group 1 ions like lithium, sodium, potassium, they are all soluble ionic compounds. So then potassium fluoride would be soluble in water. And then we have strontium nitrate and nitrates over here. All common nitrates, acetates or perchlorates, they are all soluble, meaning strontium nitrate is also soluble in water. And then we're going to be looking at our products, which is going to be potassium nitrate. All potassium group 1 are going to be soluble, all nitrates soluble. So one of our products, potassium nitrate, also soluble. And then one of the products, strontium fluoride. All common fluorides are soluble ionic compounds. And then there are some exceptions. Lead fluorides and fluorides of group 2A. Now strontium is in group 2. All fluorides are soluble except lead fluoride and fluorides of group 2A. If you refer to your periodic table, strontium belongs to group 2A. So then strontium fluoride is insoluble in water. So with that in mind, you can write down that potassium fluoride is soluble. For the soluble ones, you write AQ. This is AQ, this is AQ, and strontium fluoride would be S. And S here for the solid. Okay, that's one way, one of the charts that you can use to find out whether a compound is soluble or insoluble. Also, you can refer to this chart that I previously mentioned, that you find this in the periodic table and the handout. And in the handout, this is page 7. Okay, I just put it over here so for you to see that. So this is page 7 if you count from number 1 as your periodic table. Now, how do we use this table to find out if a compound is soluble or not? Now, our first one of our first reactants, potassium fluoride. So you're going to refer to potassium. So this is potassium and fluoride is right here. So you go across potassium and fluoride. You see here? And here in this chart, S represent soluble. So meaning if you find it as S, meaning it is soluble in water, that is AQ. And then we have strontium nitrate. So strontium is right here, strontium, and then the nitrate going to be here. Okay, right there, strontium, and this is the row for the nitrate, strontium nitrate soluble. And then one of the products, potassium nitrate. So potassium is in this column, and then the row nitrate, you meet the two, S for soluble. And then we have strontium fluoride. So strontium right here, that's one of the products. And then the fluoride is this row, fluoride right there. So strontium fluoride is I for insoluble. So that is a solid that you're going to be forming. Okay, you can refer to both of these charts or one of these, and this is available to you in the periodic table and handout, page number 7. It would be more clearer than this, okay, in a PDF file. So this is our molecular equation. I just wrote it with you guys. Potassium fluoride, strontium nitrate, and strontium fluoride is a S. And then we can write the total ionic equation where you're going to separate this into ions. That says AQ. When you are separating into ions, you want to make sure that you write how many ions and also what is the charge of the ion. So this would be 2 potassium, 2K plus. You don't just write K. You have to write K plus. And there are 2 fluorides. And strontium is 2 plus. So 1 strontium 2 plus aqueous. There are 2 nitrate ions, you're going to write that, 2 nitrate minus, and then your arrow, yield arrow, and then aqueous potassium nitrate, 2K plus, 2 nitrate, and strontium fluoride, since it's a solid, you do not break it into ions. Okay, you're going to leave it as S, and this is your total ionic equation. And what are our spectate ions? Spectate ions are the ones that you find in both sides without any change. So we have 2K plus. It has to be the same amount as well. So 2 nitrates. And then we are left with 2 fluoride, 1 strontium forming SrF2. So the net ionic equation is strontium, and we normally write the cation first with 2 fluoride forming SrF2. So this is the net ionic equation. Now, spectate ions are potassium and nitrate. So in your molecular equation, whichever end up as aqueous would end up being as your spectate ions. Okay, whichever end up as the formation of the solid would involve in the net ionic equation. Something for you to make it easy when you do your homework and your exam problems. Okay, and then the next one is ammonium perchlorate and sodium bromide. And ammonium ion, how do you write the formula again? You have to refer to the chart with the polyatomic ions. Ammonium ion is +1. Okay, and perchlorate is ClO4 minus. ClO4 minus. So 1:1 ratio ammonium perchlorate plus sodium is +1, Br minus 1, NaBr. And then it's going to form ammonium bromide and sodium perchlorate. If you refer to the chart, you will find ammonium bromide. All the ammonium ions are soluble in water. So ammonium bromide is aqueous. And all the sodium ions, remember the group 1, all the ions are soluble in water, as well as perchlorates are soluble in water. So this is also aqueous. All of them are going to be in the present in the solution as ions. So if you look at the total ionic equation, you can break them into ions. Ammonium ions, perchlorate ion, sodium ion, bromide ion, again ammonium ion, bromide, sodium and perchlorate. So what are the spectrate ions? All of them are spectrate ions, right? All ions are spectrate ions and there is no net ionic equation. Compounds remains in solution as solvated ions. Okay. Okay, so that's some examples of precipitation reactions. And the next category of the reactions that we learn is acid-base reactions. Now, acid is a substance that produces hydrogen ions when dissolved in water. We can abbreviate the acid as HX. X could be a halogen like chlorine. If it is chloride, it would be hydrochloric acid. And then it would dissociate completely if it is a strong acid to H plus ions and X minus ions. A base is a substance that produces hydroxide ions when dissolved in water. Metal hydroxide. Normally it has hydroxides. Metal hydroxide dissociates into metal ion M plus and hydroxide ion. We call acid-base reaction as a neutralization reaction. Because if you remember the pH values, acid is a lower pH, base is a higher pH, and you're going to be making salt and a water. Salt is a neutral species and then the water is also neutral. So acid and base together forms a neutral solution. Acid become neutral, base become neutral once it form water and the salt. So we call it as a neutralization reaction. There are some strong acids and weak acids. So these are the strong acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid. They are all strong acids. Meaning in the water they completely dissociate into ions. Okay. And then these are some examples of weak acids. Hydrofluoric acid, phosphoric acid, acetic acid. These are the ways that we can write the acetic acid. So these acids are weak acids because they would not dissociate into ions completely. Only a certain amount will form ions, but most of the time they're going to remain in the solution as this form. Okay, notice this form acetic acid. So this is a category called carboxylic acid. And this methyl group could be a different group. But when you recognize this COOH, Chuchu, one of my students came up with the name Chuchu. Chuchu, right? So it resembles a weak acid. And these are some strong and weak bases. Strong bases, remember we talk about that can have hydroxide ions. So group 1A, hydroxides. Group 1 has lithium, sodium, potassium, rubidium, cesium. Their hydroxides are strong bases. And then group 2, heavy group, 2A2 hydroxides. Calcium, strontium, barium, these three are considered strong bases in group 2. And then the weak base is considered ammonia and also some ammonia derivatives, meaning if you replace this hydrogen with another group, so that also a nitrogen base, so that would make it a weak base. Okay. Acids and bases as electrolytes. Strong acids and strong bases, they dissociate completely into ions in aqueous solution. So if you have acidic solution, you hook this up through the wire to the electric source, you would see since it's a strong electrolyte, the light bulb will light with the maximum light giving us. Okay. So that means strong electrolytes conduct well in solution. And if you have a weak electrolytes, which are weak acids and weak bases, they dissociate very little into ions in aqueous solutions. They are weak electrolytes and conduct poorly in solution. Now, for example, if you have a strong acid like hydrochloric acid, HCl, you put it into water, it's going to make H plus ions and Cl minus ions, chloride ions. Once it dissociate, you will not find any hydrochloric acid intact. Everything will be H plus and chloride ions. Okay. Whereas, let's say you have a weak electrolytes, for example, acetic acid. So, acetic acid, let's say the formula CH3COOH. You put this into water, it would dissociate into acetate ions only a little bit to the forward reaction, but mostly it would be in the form of the original weak acid, acetic acid. It will make acetate ion CH3COO minus plus H plus. Okay, you see the arrow, the backward arrow is longer, meaning it's only dissociate to up to a certain amount. Mostly it would stay as acetic acid. Okay, that's why since it's not going to form many ions of these, if you have a weak acid, there's only a little amount of electrolytes present, so you can see it's a dim light. It's not as bright as the strong electrolyte, which is the hydrochloric acid or any of the strong acids. They conduct poorly in solutions. Writing ionic equation for acid-base reactions. Write balanced molecular, total ionic and net ionic equation for the following acid-base reactions and identify the spectate ions. We have hydrochloric acid and potassium hydroxide. So hydrochloric acid is HCl, potassium hydroxide is KOH, strong acid and a strong base. Similar to precipitation reaction, they are going to exchange their counter ions. Hydrogen will combine with OH to form a water molecule and then potassium chloride. Okay, now hydrochloric acid is dissolved in water. Potassium hydroxide also dissolved in water. And KCl also going to be aqueous. But this newly formed water molecule, it formed as a result of the water molecule generated by reacting your acid and base. So since this water molecule is not belong to our aqueous medium, it's just newly generated, that is considered as a liquid water that came up due to this acid-base reaction. And in fact, that's going to be the product of a acid-base reaction, a liquid water molecule. Okay, so let's see how to write the total ionic equation for this. So the molecule equation, hydrochloric acid and KOH, giving potassium chloride and water, liquid water. Total ionic equation would be hydrochloric acid completely dissociate into ions because it's a strong acid. Potassium hydroxide completely dissociate into ions, K plus NOH minus because it's a strong base. Potassium chloride is an ionic compound. We saw ionic compounds completely dissociate into ions to K plus and Cl minus. And then the liquid water molecule, you do not break it into ions. Okay, now what are the spectate ions? We have Cl minus here, Cl minus, that's a spectate ion. Potassium ion and potassium ion are spectate ions. So the spectate ions are potassium and chloride. And then for the net ionic equation, we have H plus and OH minus giving you liquid water molecule. So in acid-base reaction, net ionic equation would be the formation of liquid water molecule. Whichever end up as aqueous salt would be your spectator ions, potassium and chloride. Okay. And then the other one, strontium hydroxide and perchloric acid. So strontium hydroxide. Strontium is +2 charge, hydroxide -1. So when you crisscross the charges, this is the formula for strontium hydroxide. With perchloric acid, HClO4 is going to form strontium perchlorate, and with hydrogen and OH is going to form a water molecule. And then we need to balance the equation. When you write strontium perchlorate, strontium is +2, perchlorate -1. So there would be 2 right there in the proper formula. Since you have 2 perchlorate, you have to put 2 there. Okay. And then since you put 2 there, so we have hydrogens 2 plus 2, 4. To make hydrogen 4, you have to put 2 water molecules. That will make 2 oxygens, which is 2 oxygen. There now it is balanced. So our product is the formation of the liquid water, and these all going to be aqueous. In the total ionic equation, we can break everything that says AQ. Strontium 2 plus, hydroxide 2 hydroxides, 2H plus, 2 ClO4 minus, and 1 strontium ion, and 2 perchlorate ions, and 2 liquid water molecules. So now what are the spectate ions, where you find both in the both sides the same form, strontium 2 plus, strontium 2 plus, and then 2 ClO4 minus, 2 ClO4 minus going to be your spectate ions. And for the net ionic equation, you have hydroxide and 2H plus forming liquid water. So 2 to 2 to 2. So when you divide it by 2, formation of water is going to be the net ionic equation. Okay. And then the other one, barium hydroxide and sulfuric acid. Now let's look at that problem. Barium hydroxide. Barium is in group 2, barium 2 plus, hydroxide -1. Make it barium hydroxide formula like this. This is sulfuric acid H2SO4. Now the product that's going to form between barium and sulfate forms barium sulfate, and then with hydrogen and OH going to form 2 water molecules. Now if you refer to the solubility chart, you will find barium sulfate is a solid, but let's go and see. Barium. So where is the barium? So barium is right here. That's barium, and then the sulfate. Sulfate right there, sulfate. Barium sulfate is insoluble, I, meaning it's a solid. Okay, so you have to put S for barium sulfate. And then you have the formation of liquid water as one of our products. And then whichever that says AQ, you're going to break them into ions. So the barium hydroxide ions are going to be barium 2 plus ions, 2 hydroxide. Sulfuric acid can be broken down into 2H plus and sulfate ion. Barium sulfate you don't break because it's a solid, you're going to leave it. And then the 2 water molecules also you're going to leave it. This is one of the products of the acid-base reactions. Do we have any spectate ions? So this side we have barium 2 plus, but this side as the product side we don't have any barium 2 plus. And then what about sulfate? No. So we don't have any spectate ions. And this is the total ionic equation. The net ionic equation is the same as the total ionic equation since there are no spectate ions. So what is the classification of this reaction? This reaction is both a neutralization, meaning acid-base reaction, and also a precipitation reaction. Okay? Okay. Let's talk about the weak acids in our next session. Okay? I think that's a good idea. Okay, let's stop here.